All right, let's get started. So on Friday, I think on Friday, well, on Friday's lessons posted, we talked about series circuits. All right, and so today I want to talk about parallel circuits. All right, parallel circuits. Now, series circuits are connected in series, just like the name suggests, and parallel circuits are connected in parallel. So you see it on this diagram right here, you see a resistor being connected in parallel. So resistor 1, right? And resistors can be any electronic, right? It can be light bulbs, refrigerators, anything electronic. And so that's resistor 1, resistor 2, and resistor 3. And the current flows through each resistor. And so this is a circuit connected in parallel, right? Circuits connected in parallel. Now, and again, you see an example of a series circuit and parallel circuit here. And some of you may have seen this cord, right? This cord right here. And that is if you start connecting things into this cord, they'll be connected in parallel. This is another way to connect things in parallel. Right? Most things in the world is connected in parallel. Most things in the world, mainly because of its uses. Now, again, this is the difference between series and parallel circuits, right? You see, these resistors are connected in series, right? They're connected in series, and this is connected in parallel. It's connected in parallel. And so let's talk about the cons and benefits, right? I think we talked about the cons and benefits in the series circuits lesson, but I'll say it again. So let's look at the bottom here, right? In this parallel circuit, electric current can continue, even though one light bulb is burnt out. So you see, even though that light bulb is burnt out, right, electric current can continue. So even if this wire is broken, the electric current can still continue for each other resistor, for each other light bulb, right? There are other pathways for this electric current to flow through. Whereas if you had a light bulb break out over here, then electric current can't flow through it anymore, which means that the entire thing would not be able to conduct electricity anymore. Electric current would not be able to run through any of these light bulbs anymore if one of these light bulbs was broken or if one of these wires was broken. All right. So that's where the benefits of being connected in parallel come in. So even if one thing doesn't work, it doesn't damage the rest. All right. Rather, the rest don't stop working as well. All right. And so now we get to the formula for parallel circuits. Right. So this is on your reference table, and it's a little bit different than the formulas for series circuits, also on your reference table, right, on page 4. It's a bit different. It's a bit different. So these are the circuits. These are formulas related to parallel circuits, and we'll explain. And I'll explain why they're different in just a second. Right. So let's take a look at current. If you take a look at this GIF, you'll see that, well, the amount of electrons at the beginning of the circuit, as they go through this parallel circuit right here, you'll see that the only thing that's happening is that the electrons are just getting split up. Right? That's the only thing that's happening. The electrons are just getting split up over here. And at the end right here, once this circuit comes into one, right, once they combine, you'll see that the amount of electrons is the same as the amount of electrons before. So at the beginning, the electrons moving through the circuit in the beginning is the same as the electrons moving at the end. It's just that when it's running through these resistors, it's split up. So let's go back to this formula. The total current running through this entire circuit is equal to the current running through resistor 1, right? Through resistor 1, plus the current running through resistor 2, plus any more currents running through any more resistors, okay? So this denotes current through running 1, and current running through resistor 2. All right, so that's what that formula means, and that's a little conceptually that's a little bit easier to understand than the current for series circuits. Now, let's take a look at this GIF right here, and again, the protons are not the one that's moving, right? The protons are not the one that's moving. It's the electrons that are the ones that are moving. Okay, it's electrons. Now, now let's explain this. What this formula is saying is that the total voltage, the voltage drop, the potential difference is equal to the voltage drop is the same through each resistor. Right, that's what this formula is saying. The voltage is the same for each resistor. The potential difference is the same for each resistor. It kind of makes sense because you have the same amount of electrons at the top and you have the same amount of electrons at the bottom, which means that the drop in voltage from the top to the bottom is the same. Right? It doesn't matter if the resistors have different resistances. Doesn't matter at all. The only thing that matters is the voltage drop. And so the potential difference right here, the potential difference from the top to the bottom is the same. Because again, you have these pool of electrons, it's the same, and the pool of electrons at the top is the same as well. Which means that the voltage drop is going to be the same. Alright, the voltage drop is going to be the same because the total amount of electrons at the top are equal to the total amount of electrons at the bottom. Right, the total circuit, the total current running through the circuit is the same. Alright, so the voltage drop is the same. So now let's move on to resistance. And this formula is a bit tricky to understand. You can prove it two ways. You can first understand it conceptually, which I'm going to explain, or you can prove it using a formula. Alright, so let's talk about it conceptually. Alright, let's talk about it conceptually. So look at this escalator right here and these stairs. So you have a certain amount of electrons. Let's call these people humans electrons, right? Let's call these humans electrons. Let's call this escalator a resistor, right? Let's call these stairs, escalators, a resistor. And so, well, there's clearly a bottleneck here, right? If you ever been at a train station, maybe like a Penn Station, or you're on the 7 train in maybe Grand Central, 42nd Street, before the pandemic, you see there's a bottleneck, right? People are just rushing towards the escalators and there's not enough room. And so you have all these electrons wanting to go up somewhere, wanting to go to the other side, right, through these resistors. But there's only a certain amount of resistors that they can travel through, right? And it's bottleneck. There's only a certain amount of electrons that can pass through each resistor at a certain time. Maybe the stairs accepts less resistors, so there's greater resistance here, so fewer electrons can go through these stairs, and maybe this escalator has a lower resistance, meaning more electrons can go through these escalators at a single time. Well, how do we decrease the resistance, right? Clearly, there's a huge bottleneck here, and that means there's a high resistance. Well, how do we reduce this bottleneck? How do we reduce this resistance to electrons that want to go through these resistors? Well, what we can do is we can add a third resistor, right? We can add a third escalator. If we add a third escalator, now more people can travel through to the other side. And if we're relating humans to electrons, if we're adding another escalator here, if we add another resistor here, that means more electrons can go through, can pass through to the other side now. So what you've done when you add a third resistor is that you've reduced the resistance. The overall resistance of the circuit, you've just reduced it now. You add this third resistor, more humans can travel through, more electrons can travel through the circuit. So the more resistors that you add, so again, down here, the more resistors you add, the more electrons can flow through, which reduces the overall resistance of the circuit. And so that is your analogy right there. And so this is on the right hand side, that's the proof for the formula. All right, that's the proof. All right, so now let's move on to solving problems. All right, so number 1. So parallel circuits. A combination of two identical resistors is connected in series and has an equivalent resistor of 10 ohms. So in series, so let's actually rewrite this. So in series, your equivalent resistance is 10 ohms, right? That's your equivalent resistance. And so what's the equivalent resistance if you connect these two same resistors in parallel? So in parallel, they want your equivalent resistance in parallel. Okay, they want the equivalent resistance in parallel. And so we know in a series circuit, if you look on your reference table, in a series circuit, the total resistance is R1 plus R2. Right, that's your total resistance. And in a parallel circuit, your your equivalent resistance is RQ is equal to R1 over R1 plus 1 over R2. So it says a combination of two identical resistors, right? They're identical resistors, which means that they probably have the same resistance, which means that if this is 10 ohms, then R1 is 5 and R2 is 5 ohms. Okay, so R1 is 5 ohms and R2 is 5 ohms as well. And so now our equivalent resistance right here, right? Our equivalent resistance right here is going to be 1 over RQ is equal to 1 over 5 plus 1 over 5. So R1 over REQ is equal to 2 over 5. Well, how do we solve this? We're going to cross multiply, right? 1 times 5 is 5. Let's actually give us a little bit more room. So again, 1 over RQ is equal to 2 over 5. Alright, so you cross multiply 1 times 5. You get 5. 2 times RQ is 2 REQ. And I'm sure you guys can do the math, right? So your equivalent resistance, if you connect two resistors, identical resistors together in parallel, then your equivalent resistance is 2.5 ohms. All right, which makes sense because your overall resistance should be less. So number 2, a 3 ohm resistor. A 3 ohm resistor, so R1 is 3 ohms, right? I mean, you don't really need knowns for this. R2 is 6 ohms. They are connected in parallel across a 9-volt battery. Which statement best compares the potential difference across each resistor? So what is the voltage, right? Potential difference is your voltage. Which statement best compares the voltage drop or the potential difference across each resistor? And if you took a look at the GIF, right? If you remember the GIF, the voltage drop is the same. The voltage drop is the same. So voltage drop V1, V2 is the same across resistors connected in parallel, right? This is your battery. So the voltage drop is the same across each resistor because the potential difference is the same. The voltage from the top and minus the bottom is the same. So it doesn't matter what the resistance is, your potential difference across each resistor is the same. And so it's one of those answers. You'll figure it out. I believe in you guys. Number 3. What is the total current running through a circuit consisting of 6 operating 100-watt lamps connected in parallel to a 120-volt source? This actually isn't a parallel question, but whatever. So your power in a circuit consisting of 6 operating 100-watt lamps. So each 6 operating, so each lamp has a wattage of 100 watts. Okay, so that means the total power, now is 600 watts. All right, so 600 watts, that's total power. And the total voltage is 120 volts. Okay. And we know that the formula for power, right, on your reference table, if you take a look for formula for power, is V times I. So 120, 600, I divided by 120, and you get a certain number, and you get 5 amps, right? So that's your answer. 4. 3 identical lamps are connected in parallel with each other. If the resistance of each lamp is X ohms, what is the equivalent resistance of this parallel combination? 3 identical lamps, so connected in parallel. The resistance of each lamp is X ohms. You guys should get used to drawing circuits. So X ohms was equivalent resistance, so you know your equivalent resistance in a parallel circuit is this, right? Maybe I'm taking up too much space, so let's actually erase all of this. I am taking too much space. So 1 over RQ, or REQ, to the 1 over R plus 1, plus R plus 2, plus 1 over R plus R3. And so we know the resistance of each lamp, right? Resistance 1, resistance 2, resistance 3 is equal to 1 plus x, 1 over x, plus 1 over x, plus 1 over x. 1 over REQ now. And you get 3 over x, and then you cross multiply, okay? You cross multiply and you solve for REQ. And there's your answer. You guys can solve it yourself. An electric circuit contains a battery, 3 lamps, and an open switch, and as represented in the diagram below. When the switch is open, there's an electric current in what? So when they say switch is open, open means it's not connected, right? Switch means when it says open, it means not connected. This means open. When the switch is closed, right? When the switch is closed, that means it is connected. So the switch right here, that means it's closed. But when it's open, the only thing that can flow through, the only path that electric current can flow through is through lamp 1, right? That's the only thing it can flow through. That's only if it's open. All right. But once you connect the circuit and you close the circuit, you close the switch, then the electric current can pass through each of these lamps. But when the circuit is open, the only current that can flow through is through lamp 1. All right, so that's your answer. In which circuit would current flow through resistor R1 but not through resistor R2 while switch S is open? In which circuit would current flow through resistor but not through resistor R2 while switch S is open? So if you take a look at these, uh, if you take a look at these options, it should be fairly easy to figure out whether or not which current is going to flow through something. Let's work our way backwards, actually, though. Let's look at D, right? At D, your switch is down here, right? Your switch is down here, which means that the only thing current is going to flow through is resistor R2 because that's the only thing connected, right? That's the only thing connected. So the only thing that's going to flow through is through current through resistor R2. So current is going to go this way, this way, this way, this way. Now let's look at option B. Option B is saying that the switch is all the way over here now, and this is open, right? That's what B is saying, which means that there's no electric current running through this circuit at all. It can't go through R1, it can't go through R2, so it can't go through the circuit at all. So there's no electric current in choice B. Choice C is the same exact thing. Choice C is a series circuit, and since the circuit is broken in the middle, no electric current is running at all. And so that only leaves us with choice A, right? So there is an electric current running through R1, and there is no electric current running through R2 because the circuit is not connected, right? The circuit is broken, is not connected. But once you do connect it, you will have an electric current running through R2. 7, as the number increases, what happens to equivalent resistance? I talked about this conceptually, right? What happens to your equivalent resistance? I talked about this conceptually. If you've been paying attention, if you listened, instead of just rushing to the answers, switching to the end of the video to only look at the answers, then you should be able to figure number 7 out. Number 8, in the circuit diagram shown below, what is the current running through the 4 ohm resistor? So for 8, you're going to use this formula right here. R is equal to V over I. And you know your voltage is 12 volts. And you know your resistance is 4 ohms. And you know your current, so you can figure out what your current is, okay? So that's easy. You guys can do the math. Yeah, you guys can do the math. All right, good stuff, good stuff.